Welcome to the Deep Dive, the show where we grab the newest, most aggressive claims in deep technology, stack up the research, and really figure out what's driving the engine under the hood. Today, we are diving deep into the world of logic synthesis optimization.
And this is an absolutely foundational problem in hardware design.
Hmm.
I mean, when you're trying to build an electronic circuit, you need a sequence of transformation steps, really shrink its physical size, its area, and cut down the signal travel time or delay. But finding that perfect sequence it's brutal.
Brutal because you are searching an exponentially large, discrete space. This means all the traditional search methods, we're talking reinforcement learning, RL, multi-arm bandits, MAB, even Bayesian optimization, they're just incredibly computationally expensive. The sources we have, they call them out as suffering from, and this is a quote, considerable overhead and inefficiency.
Right. And they're slow because they have to constantly test sequences, either in the real world or in these very slow simulations. It's a very
Yeah.
sequential stop and start process.
And that's where the headline grabbing breakthrough comes in. The solution they're proposing is pretty radical. It's stop searching the discrete space altogether and instead move the entire problem into a continuous latent space.
Yeah, the core idea is to use an explicit gradient for speed, something RL or MB often lack. But then you have to pair that with a really powerful generative model.
And that model is a diffusion model.
Exactly. The thinking is, look, we can optimize lightning fast in this continuous space, but we need a rock solid mechanism to make sure whatever mathematical optimum we find actually translates back into a physically feasible sequence. That's the fundamental problem they're trying to solve.
And the numbers they report are just astounding. They claim they achieve better QRSO, lower area and delay, while improving the efficiency of the whole process by a factor of 5x up to 130x.
It is the kind of number that, makes venture capitalists lean forward in their chairs. But that massive claim
Mhm.
that brings us to our mission for this deep dive,
Huh.
we think that efficiency gain is, well, it's deeply misleading.
Misleading how?
When you really dig into the sources, it becomes clear that this method introduces massive pre-optimization overhead, algorithmic complexity, and a degree of extreme fragility that those headline numbers just completely gloss over.
Okay, let's unpack this. Before we even get to the critique, we have to understand how this system is built. It sounds incredibly complex. What are the two pieces of this two-headed dragon framework?
It's a very delicate fusion of two advanced deep learning models, and that combination is precisely what creates all the fragility. Each component has its own massive training requirements, its own failure modes, and a lot of mathematical approximations just baked right in.
Okay, so component one, that has to handle the quality of the result, the QR. What exactly is that model doing?
That's the QRR surrogate model, what we'll call CentiMXers. Its job is pure prediction. It's trained to estimate the final circuit quality area and delay from an input, $6, which is the sequence embedding. But its most critical job isn't just predicting. It has to generate the explicit optimization gradient. That gradient is what tells the search which way to move to lower the area or delay.
So that's the speed engine. Okay. Now, component two, that's the complexity engine, the diffusion model. Why do they need such a sophisticated generative model just to make sure things are, feasible?
Because continuous optimization on its own is reckless. If you just follow that QR gradient, you immediately wander off into some mathematical space that doesn't correspond to any real executable sequence of transformations.
Right. It's just math, not physics.
Exactly. The diffusion model, epsilon theta, equate d 2 t at t, is trained to basically map the landscape of all feasible sequences. It acts like a constant magnetic field, always pulling the continuous variable back onto the path of things that actually make sense.
So the whole optimization loop is this push and pull. You're trying to find the optimal sequence, $6 lols, by minimizing two things at once. The QOR prediction and this feasibility discrepancy, the PEL plus HX.
Precisely. And the elegance of the technique is that they manage to merge these two conflicting forces, the push to reduce area and the pull to stay feasible, into one single iterative update rule. It combines gradient descent for QOR with these denoising steps for feasibility. It's a neat mathematical trick, but we have to look at the hidden costs.
Let's do it. Criticism one, the massive upfront overhead. This seems to be the main reason that 5x to 130x number is so suspect.
It's the classic shell game. I mean, the efficiency gain only measures the execution time of the final optimization loop. It completely ignores the enormous mandatory effort required to set the system up in the first place. And they just brush it off as a one-time effort.
And what does that upfront effort actually look like? This isn't just, downloading a small model from GitHub.
Oh no. It's an industrial level data collection task. Both models, the surrogate and the diffusion model, they need huge training sets. For their experiments, they had to collect and process 20,000 randomly generated sequences. Just think about the compute cost and time for that, just to get the data.
And this model isn't a general one, right? This is the killer point for anyone trying to actually use this.
It's not generalizable at all. The sources state it very clearly. This entire pre-training process has to be performed for each target circuit. They say, and I'm quoting here, for each circuit, we train a corresponding surrogate model and a diffusion model, which takes about 11 minutes and is a one-time effort.
Wait, 11 minutes per circuit. So if I'm a design house trying to optimize 100 different circuits this week, that's 1,100 minutes.
Right.
That's nearly 18 and a half hours of just model training before I even get to see that supposed 5x speed up.
Exactly. You've just hit the core flaw in their entire efficiency comparison. The baselines they compare against, like RL or BO, they actually learn during the optimization. They improve as they search. They don't have this massive 11-minute per circuit tax you have to pay just to get started. That setup cost just evaporates any downstream speed advantage.
And there's a fragility here too, isn't there? You are completely at the mercy of those initial 20,000 random sequences. If that data set isn't a good representation of what's possible for that specific circuit, your optimization is just doomed from the start.
It is. The whole system is built on this very rigid foundation. If your training data is flawed, that 130x speedup just means you get to a bad and non-optimal result 130 times faster.
Okay, here's where it gets really interesting. Let's move to criticism two. The unreliable gradient and the intractable math. The whole promise of this is that stable, explicit gradient. But is it actually stable?
It turns out no. It's fundamentally unstable in practice. The surrogate model, the one that provides the steering gradient, is operating inside this iterative diffusion process. And diffusion, by its very nature, introduces noise. So the surrogate model is trying to make predictions based on these noisy latent variables, $6.
And the sources admit this was a problem for their speed engine.
They do. The model struggles to give an accurate prediction inside that noise envelope. And the proof is the fix they had to implement. They have to use a separate noise-free version of the variable using a technical maneuver called the reparameterization trick, just to feed the QRR model and get, quote, a more accurate gradient.
So just to be crystal clear for everyone listening,
Yeah.
the very source of the speed, that explicit gradient, is so unreliable that they have to pause the process, use a computational trick to create a clean variable, get the steering direction from that, and then apply it back to the noisy process.
That's a perfect summary. The fact that they need that workaround proves the primary gradient source is inherently unreliable.
Wow, okay, that's the QOR side. What about the math debt on the feasibility side, the HDO next term? Why can't they just calculate the gradient of that directly?
Because it's mathematically intractable. Computing HX directly would require you to integrate over the entire distribution of all possible sequences. That's a computationally impossible task. It would be even slower than the discrete search they were trying to replace.
So they've just traded one impossible problem for another. They can't calculate the real feasibility gradient. So what do they do instead?
They incur what we're calling tractability debt. Instead of computing the true gradient, they optimize a variational bound and approximation. And that approximation is implemented by the entire complex training process of the diffusion model. You've replaced one hard calculation with the entire mandatory infrastructure of a second, very sophisticated deep learning model.
That's a critical insight. They didn't solve the hard math problem. They just built a massive approximation engine that takes 11 minutes of training per circuit to get around it.
Precisely. And if that approximation engine isn't perfect, the whole system just crumbles. Which brings us right to criticism 3, extreme fragility. The diffusion model isn't just a helper here. It is the sole guarantor of solution quality.
We've established the continuous part is fast but reckless. So what happens if you just turn off the diffusion model?
Catastrophe. Pure catastrophe.
Yeah.
The whole advantage hinges on that model correctly enforcing feasibility. Without it, the optimization, guided only by the QOR gradient, just flies off into regions that correspond to impossible or just totally useless circuit designs.
And the sources give us hard proof of this in their ablation study. Let's go over those numbers again because they're really staggering.
Yeah. In the successful run with the diffusion model working, they get a QR area of a very respectable 11,900 diesel variable dollar. A good result.
And then they disable the diffusion model.
And the continuous latent variables immediately, quote, deviate from feasible embeddings. The optimization becomes meaningless noise, and the final QOR area result just balloons to $22,654.15 model.
That is almost double the area. A 1.1 times larger result. This isn't just a little worse, it's a total system collapse.
It's absolute proof. The high-speed continuous optimization part is fundamentally useless on its own. It is completely reliant on the constant, heavy-handed intervention of the diffusion model, the same component that costs 11 minutes per circuit and carries all that technical debt. You cannot have the speed without the complexity. They are completely coupled.
Given all this mandatory complexity, let's wrap up with criticism for just the difficulty of tuning and deploying this whole thing. It sounds like an operational nightmare.
It is. It introduces practical headaches that the other methods just don't have. You're constantly trying to balance two conflicting objectives in that loop. You're trying to minimize QRR, which pushes you toward unstable areas, while you're simultaneously trying to minimize the feasibility discrepancy, which pulls you back to safety.
And that balance is controlled by just a handful of very sensitive coefficients, right? The stellas and omega in their final equation.
And tuning those is an art form. If you make the QRR component too aggressive, you overwhelm the feasibility constraint and you get that 2x larger area result. You crash the system. But if you make the feasibility component too strong, you just stop optimizing QR. You go nowhere. Misalignment is catastrophic.
And that's before you even get into tuning the diffusion model itself.
Exactly. The diffusion model needs careful tuning of noise parameters, conditional distributions. It has to run through 500 steps in this case. If that model is even slightly miscalibrated, if its approximation is poor, it immediately leads to that same disastrous QR result.
Let's use that ship analogy again for the listener. The traditional methods, RL or BO, they're slow, sure, but they're like a reliable ferry, always moving between known islands. They're slow, but they don't sink.
This new method is that high-speed jet boat we talked about, but now we see it clearly. It's got two perfectly synchronized engines. One is the speed engine, the QRR minimization. The other is the complex diffusion model, this compulsory gyroscope constantly fighting to keep you on course.
And the danger isn't that it's slow. The danger is that if those two engines are misaligned because you tuned eta and omega wrong, or if the gyroscope engine itself fails because of some complex noise tuning, the jet boat instantly flies off course, crashes, and gives you an outcome, that 2x larger area, that is far, far worse than the slow ferry would have ever given you.
The high speed comes at the cost of extreme fragility. That's the trade-off.
So let's quickly summarize. First, high pre-optimization cost, 11 minutes of mandatory setup per circuit, training on 20,000 samples, a cost that's totally ignored in the efficiency claims.
Second, unreliable gradient and tractability debt. The speed engine is unstable and relies entirely on a complex approximation, the diffusion model, to even function.
Third, extreme fragility. The continuous optimization is useless on its own. The diffusion model is the mandatory guarantor of quality, and its failure leads to a nearly 2x worse result.
And fourth, tuning complexity. The whole system requires this incredibly sensitive calibration of competing objectives and noise parameters, making it very risky to deploy.
So what does this all mean? The claims of revolutionary efficiency, they're only visible if you completely ignore the huge mandatory per circuit upfront investment and all this inherent instability.
Which leads to a really profound question for you to think about. Since the core efficiency driver here, the continuous optimization, is fundamentally unstable and literally non-functional without the constant heavy-handed intervention of this sophisticated generative model, does that speed up during the final run truly justify the mandatory, fragile, and massive dependency on deep learning approximations and huge setup costs for every single new task? That's the trade-off you have to evaluate.